Daniel's internal supervisor is Mike Wotton, who has joined us. And also joining us in the room is Melanie Wheatley, Wildland Fire Research Scientist at MFC. Dan.
Thanks, Peter. Hey, everybody. My name is Daniel Lowe. I'm going to be presenting my capstone research characterizing forest structure and its impact on Airtanker drop penetration using airborne LiDAR. So can you guys hear me all right back there with the speaker? Beautiful. All right. First, let's start off with an overview of wildfire in Canada. So as I'm sure a lot of us are aware, fire is a naturally occurring process in Canada, particularly in the boreal forest. Canada hosts over 300 million hectares of boreal forest, and it represents over 75% of our forested area. Over the last 10 years, the country has averaged around 400 million hectares burned and roughly 5,300 fires per year. Half of these fires are typically human-caused, with the other half being caused by lightning, although lightning-caused fires typically represent 85% of the area burned. Wildfire management in Canada is a provincial responsibility, with the goals of management being twofold. The first goal is to protect communities' property and resources from wildfire, and the second goal is to allow fire to play its ecological role on the landscape. So when a wildfire is first discovered, the response phase begins with what we call initial attack. Initial attack typically consists of a ground crew supported by aerial suppression. Ground crews carry out aggressive initial attack operations to limit or reduce fire intensity and prevent fires from escaping. The role of aerial suppression is to support these containment efforts by reducing challenging fire behavior to a level that ground crews can then get in safely and effectively manage these fires. Aerial support can occur in two ways. The first way being direct attack, which is when an air tanker drop is placed directly on the active flames to knock it down to the ground and immediately reduce fire intensity. And the second one being indirect attack, where a drop is placed ahead of the advancing fire, saturating unburned fuels and reducing their combustion potential, which slows the rate of spread and provides ground crews with a chance to achieve suppression objectives. So nearly 3 decades ago, a paper from Hirsch and Martel identified a critical gap in our understanding of aerial suppression effectiveness. And kind of fast forward to the last 10 years or so, we've built on this, not we, but literature has built on this need, first by conducting a major field experiment in Dryden, Ontario from 2017 to 2019, where air tankers conducted drops on an open airstrip and within a closed canopy jack pine stand to assess how different environments alter drop footprints. Following this work, the reference guide to the drop effectiveness of skimmery and rotary wing air tankers, also known as the Blue Book, was produced to provide relative comparisons of air tanker performance within the context of the North American boreal forest. Since then, Wheatley and Associates have expanded the suppression effectiveness literature by documenting how air tanker drops generate transient relative humidity bubbles within forest stands and can affect fire behavior. And more recently, they've applied infrared imagery to evaluate the impacts of aerial suppression on fire behavior. So we know that forest structure shapes micrometeorological conditions, yet historically these characteristics have been quantified through field measurements or have been difficult to capture using traditional remote sensing. Light detection and ranging, also known as LiDAR, has increased this capacity. LiDAR is a remote sensing technology that maps forest structure by emitting millions of laser pulses and measuring the time it takes for each pulse to reflect off vegetation or the ground, creating what is called a point cloud. These point clouds allow us to quantify the three-dimensional complexity of forest structure, providing information on fine-scale forest vegetation, which has increased modeling capabilities for within-stand micrometeorological processes, such as wind reduction factors or throughfall and canopy interception, which is what we're going to be looking at today. A key component of understanding aerial suppression is recognizing how the environment in which a drop occurs influences the drop itself, and therefore its ability to alter fire behavior. While research on drop footprints exists, most experimental work has taken place in the open environment, despite the fact that operational aerial suppression takes place largely in forested environments. So the goals of this research project are to first examine the relationship between forest structure and drop footprints in a closed canopy jack pine stand compared to open field conditions, and to second, to develop a LiDAR-based canopy intercept model that can help predict air tanker penetration and effectiveness under various stand conditions. The two air tankers of focus As you can see here are the Canadair CL415, which has a tank capacity of roughly 6,100 liters, in which Ontario has 9 of these air tankers, and the second one being the DHC6 Twin Otter with a tank capacity of roughly 2,100 liters. Ontario has 3 of these air tankers. This has been a big project. In the scope of this capstone, I'm looking at mainly research objective 1, and that is what we'll be talking about today. So the field data collection. Air tanker drop data was collected during those 2017-2019 field experiments that I mentioned earlier using the cup and grid method. Cups 4 1/4 inches in diameter were placed roughly 3 meters apart to form a grid of about 300 cups. Drops took place at both an airfield site representing the open environment with no forest structure and in a closed canopy jack pine stand. After each air tanker dropped, the amount of water captured in each cup was recorded in millimeters. Each cup location was surveyed using precision GPS, allowing the drop footprints to be digitized for spatial analysis. Water depth was measured using the visual cupping grid method, in which a reference sheet is placed underneath each cup, and the water is referred to volume markings on that reference sheet. In total, 82 drops were performed for both aircraft. Of these, 36 were digitized and 28 were deemed valid and used in this research. A valid drop means enough of the drop footprint hit that cup grid to be representative of that air tanker's drop footprint. Lastly, we conducted a LiDAR scan with the DJI drone of the jack pine stand to then quantify and characterize forest structure. So this slide is a brief overview of the 5 steps that I did in my analysis, but I will take you on a little visual journey through each one of the 5 steps here to help everybody understand this. So first on the left here, you can see the raw cup data digitized, where each one of these points is one of those cups that got measured in the field. That was then interpolated to make drop footprints for each drop, as you can see on the right there. That drop footprint, which had the center point and center line identified, were then spatially normalized and rotated to a new space where they could then be stacked and compared. And with those stacked and compared drops, I was able to create these airfield averages, which I then used for inputs as the gross precipitation inputs for each aircraft. In terms of the LiDAR metrics, we use the LiDAR scan to calculate multiple metrics, with the 2 primary ones being plant area index and plant area density. Plant area index is a 2-dimensional metric that measures the total one-sided area of plant material per unit of ground, with plant area density being a 3-dimensional volumetric counterpart to plant area index, estimating biomass as meters squared per meters cubed within 1 meter vertical bins. For this study, plant area density was summarized into 3 vertical layers: surface, subcanopy, and canopy. And you can see kind of on that right diagram there's our sampling cup and how we took a vertical sample above each cup. To model canopy interception, I use the average airfield drop as the gross precipitation input, as shown on the right there. That's what's coming out of the plane. The amount of through-fault is the amount of water in each of the drops recorded in the canopy site. I then calculated the absolute amount of water intercepted, the proportion of water intercepted, and the relative amount of through-fault at each cup. That was done at a cup level. At the drop level, I calculated the medians for each of these through-fault metrics, as well as the coefficient of variation, which is the standard deviation divided by the mean, which calculates the amount of variation that occurs within each drop footprint. So moving into our results, let's start with the nice, simple, logical one. The amount of water in the canopy drops is significantly less than what was on the airfield sites. Okay, that's great. We know that forest structure intercepts water. That's a good starting point. I tested this with a Wilcoxon test, and there are 2 significant values for each one of the aircraft. Secondly, unfortunately, I found there was no significant relationship in this data between the LiDAR metrics and canopy penetration, whether using the absolute or the relative metrics. This does not suggest that canopy has no effect. Obviously, rather it indicates that a significant relationship was just not found in this data set. This could be due to several factors, including a relatively small sample size. There wasn't that many drops in the grand scheme of things made on the canopy site, but also it was a relatively homogeneous forest stand as it was a maturely stocked jack pine stand. Also, the relative amount of through-fall did not differ significantly between two aircraft. We do, however, see a significant decrease in the coefficient of variation for both aircraft and the canopy site. Recall that the CV is the standard deviation of the drop divided by its mean, and it's a measure of variability. The higher CV seen in the airfield drop is reflective of those distinct, clear contours as you move away from the drop center. Under the canopy, the forest structure acts as a smoothing filter and produces a more homogeneous drop footprint, decreasing the standard deviation, which is the range of water distribution, faster than the decrease in the average amount of water. Okay, so what does this mean? Overall, the analysis shows that stand structure did not exert a strong direct effect on the relative or absolute amounts of throughfall. However, a consistent pattern does emerge in the absolute water volumes. Areas receiving higher gross precipitation, particularly the drop centers, also exhibited the highest absolute canopy interception. This reflects a simple but meaningful relationship with this data. The more water that was delivered, the more water that was stored in the canopy. Excuse me. Median relative throughfall was similar between the two aircraft. It was 42% for the CL-415s and 39% for the Twin Otters, with no statistically significant difference. This suggests that aircraft type alone does not determine penetration efficiency. Rather, both aircraft lose just over half of the amount of water delivered above the canopy. Importantly, these throughfall levels have implications for suppression thresholds. The reference guide to air tankers identifies 0.5 mil as the minimum ground delivered amount of water to reduce fire behavior in medium intensity surface fire in a jack pine stand. Looking at this Twin Otter drop, we can see on the bottom right here that the drop maximum does not exceed 0.5 millimeter, suggesting that you see reduced efficiency in its suppression effectiveness at this moderate surface fire intensity. Because canopy interception reduces drop coverage of a Twin Otter to under 0.5 mil, this research suggests that fire managers will need to plan to stack drops once that fire line intensity reaches intensity class 3 or higher. It has broader implications for containment probability, air tanker sequencing, and safety of ground crews if you're working with Twin Otters. The results also indicate that air tanker choice should reflect stand conditions. The CL-415 with its larger drop capacity is better suited for dense conifer stand as it delivers a higher absolute amount of water. Conversely, Twin Otters, if you should be prioritized in open fuels such as grass fires, where interception is not really relevant and lighter drops can still achieve effective ground coverage. Next steps are developing that predictive LiDAR model. Although there are some kind of assumptions and things we need to consider when looking into that next step, this analysis kind of relies on several key assumptions. First is the drop centers are assumed to be the most accurate anchor point in which we should overlap those drops spatially. Second, drops were treated as if they traveled straight down from that airfield average into the canopy drop footprint, which there's a lot of momentum behind those drops. That might not be an accurate assumption to make. And looking at future research, since we found no significant relationship with the LiDAR metrics and the amount of throughfall here, we should look at different variations of the LiDAR metrics calculated, such as grain size, which is like the horizontal resolution, or overall voxel size, which is a combination of horizontal and vertical resolution of the sampling squares, as well as looking at alternative metrics, such as lacunarity, crown porosity, or structural complexity indices. Also, we could look at potentially tree-based metrics as opposed to what was used here was voxel-based metrics, as in the canopy interception and throughfall literature, people often look at kind of like distance from tree stem as a metric of how much water penetrates. I would like to acknowledge Dr. Mike Wotton and Dr. Melanie Wheatley for supporting this research. From my internship, Matt, Colleen, Darren, Andrew, and the rest of the wildfire science team has been very supportive, and I really appreciate all the insights they provided me over the last 8 months. Faculty of Forestry and my partner, friends, and family, as well as the 2024 MFC cohort.
Thank you, Daniel. Question to Melanie Wheatley from the Ministry of Natural Resources.
Great presentation, Daniel. Can you talk about how you would potentially expand this research as we move forward in fire management with considering mitigation measures, field routines, et cetera, and trying to understand how effective we are at suppressing fires when we also understand how can you tailor your research to maybe address some of those questions using the methods that you showed us here?
Yeah. Am I given the option of doing more field experiments? Okay. Yeah, that would absolutely be something that I would encourage. Whether that be doing drops in like a standard spruce stand, or this stand was stocked 1,000, 2,000 stems per hectare. If we then get a stand that stocked, say, roughly 500 to 600 stems per hectare, something that's significantly reduced, I think we should do field experiments in there. Given that the LiDAR data did not show a signal, and the drop footprint interpolations were quite useful in seeing these condition differences, I think that doing drops under different stand types and stand densities would be very useful.
Yeah, thanks, Dan. Couple of questions. Definition, what you talked about stacked drop, like you talked about the smaller tanker, the Twin Otter, and how it wasn't dropping all that much water, so you'd be able to deal with anything much more than a lower water. I talked about stacking drops. Can you explain that a little bit more? And then, again, yeah, can you explain that just a little bit? Might mean, is it something that happens?
Yeah, like what stacking drops is.
Yeah.
Yeah. So stacking drops is to achieve suppression goals in more challenging environments that, it's not like once that fire breaches a certain threshold, the Twin Otter is just all of a sudden not useful. You can stack drops on top of each other to achieve higher coverage levels, essentially doubling up and putting two drops in the same place to compound the effects of the drop and limit higher fire behavior. Sorry, what was the kind of the second question there?
I don't know if that is.
Okay.
So, I mean, is that common practice? Are you aware of that? Or I don't know whether you know, how much you got into all of that in your insertion. I'm curious.
Yeah, I'm not sure if stacking is common practice too much, but I do know, obviously when you're building your fire line with aerial suppression, you are achieving a certain amount of overlap to make sure you kind of get a consistent coverage level and you maintain consistent, there's a consistent amount of water being delivered to that fire line. I'm not sure how common it is to actually stack drops in one place.
Further question, if I can, Peter. I can go on. So this, you talked about, and actually in your talk, you sort of sometimes talked about things as rainfall, right? But it's that, not what you're measuring, right? But we're using these drops that were happening from, in the forest stands, at the same time that they were happening on the airfield there, as somewhat as an analogy that way, where you can expand on that. How do these drops from a tanker differ, say, from rainfall, right? Lots of throughfall, lots of kind of interception rainfall. I know we've reviewed it all today, but how do they differ from, just qualitatively that way? How do they drop?
Yeah, absolutely. So first off, Airtanker drop is kind of a discrete event. It doesn't happen over a period of time. It happens and the drop is in the canopy, whereas rainfall happens over a time period. And in rainfall interception, there is kind of this inflection point of canopy saturation where at first the canopy absorbs a lot of water, and then once it hits a certain threshold, say it's usually around 10 to 15 mil in the literature, it starts to have an increased amount of throughfall because that canopy is fully saturated. and now more water is getting through. Whereas with all the drops I've looked at with the Airtanker research, not a single one of those drops got even close to that 10, 15 mil threshold. So they're all, you could say, in that high canopy absorption state where the canopy is absorbing a lot of water because you don't have that temporal scale for that water delivery to persist.
What is the deepest part of a drop? Like, I can't remember if you have one of those, can you back up to, one of the interpolations saying,
Yeah, so for this,
can you just walk us through that, like, based on what you just said?
yeah, absolutely. So in looking at the CL 415 one on the left here, that deep centers at maximum just under 2.5 mils deep. And kind of to link it to what I was talking about with those coefficient variation. As you step out, there's a lot of variation in the drop as a total because each area has its distinct little, nice binned contour that coverage level is at. I mean, this was in the airfield site where there's no interception happening at all, but yeah, this compared to a rain event is a big storm that say lasts 10 hours. This is a very small event in comparison.
Yeah, no, I would think that's another one, right? Like this drop is happening in 3 seconds, essentially, versus the rainfall that might last for a month. And I don't think, I don't know if you guys showed him some of that, the video, the GoPro video, but it also a lot more violent in terms of how canopy and the shaking some of that water.
Yeah.
Out of the canopy. So wait, dog would shake itself off. Probably got a little bit of different character moving now. Anyways.
Yeah, it's just because we're on the slide right now.
Go ahead.
So here, this slide here, these are interpolated drop footprints from your individual platforms that I showed a couple slides ago. Can you talk about if you think that any of the results were biased to your interpolation method? You said you used thin plate splines. Did you try any types of other interpolation methods, and were they much different?
Yeah, I tried I think 2 or 3 other interpolation methods, and they're all quite different in what they revealed. The thin plate spline is definitely the most aesthetically pleasing. It's kind of the most smooth representation of that drop footprint, which is great for looking at the data, but it might not be the best for representing those actual measurements that were in each cup. But this is incredibly noisy data, so I think making a little bit of an assumption there to clean it up and make some assumptions is didn't help with the planetary density relationships, but I think it helped with other parts of the analysis for sure.
Yeah.
Who has a question for Dan? Oh, say hello.
Yeah, since it was already, the mic was already here. You mentioned we had a bunch of assumptions like average, like airfield and things like that. But do you think that the true fall and penetration rate would change if you depending on the distance the water was dropped from?
That's a good question. Yeah, like if the drop occurred higher above the canopy per se.
Higher or lower?
Yeah, I think that, I mean, these drops all occurred at what they typically drop at operationally. I think if they did drop higher, you would get more drift. If there was a fire happening, potentially more evaporation. I think that you would see a difference in those through fall results for sure.
So this standard, if the standard you drop it from here, right?
Yeah.
Thank you.
Thank you. Really, really great presentation. I was wondering, if you were given enough money to do this again, you were in charge of designing this experiment. Are there additional data that you would consider including that would allow you to better answer the question, maybe fill the gaps that you're struggling with, voice, etc.?
Yeah, that's a great question. I think something that kind of like a high precision GPS tracker in each of the aircraft, so you could see the actual flight path over the cup grid. Might help understand, okay, and then and also like kind of recording the release point and being okay, that drop was released here and it drifted to here. It will help you understand that the angle of which that drop is penetrating the canopy. That would be, I think, one of the big things. I was thinking earlier, like it could be good to potentially like make sure you get a range of different plant area index values in that site, but also like, this is the standard jack pine site, so you don't really want to change in that aspect. So I think adding that flight tracking data would potentially be helpful for understanding like that angle of penetration into the canopy, and then you could potentially change how you're aligning that canopy drop under the airfield drop to hopefully get a better signal.
Amazing presentation, Daniel. Unreal, the work you've done. Just a question, depending on the stand and the stems per hectare, what do you think the overall canopy closure is? Let's say if you use an anemometer or can any of the LiDAR data capture that, and then does that affect any of your data, the variable that you're accounting for?
Yeah, so the canopy closure for the stand is about 90%. I did calculate gap fraction. It also was not significant, unfortunately. But yeah, I think if you have a more open canopy, you're going to get more water penetrating.
Thank you.
We have Sean.
Uh-oh.
Reliable scrutiny. Better than a button.
I wonder whether your data could be used to get at kind of drop mechanics and whether that can be further optimized, because you think you get, say, a rounder field if you flew into the wind or you had reduced speed, or if there's a kind of scope to change the geometry of the dropping mechanism. If you're missing this kind of 0.5 millimeter target by a slight amount, maybe there would be adjustments, and I wonder if you could inform that kind of drop mechanics. It could be, really good thing to apply.
Yeah, that's a great insight. Thank you.
So what do you think?
Oh,
Like this, so rounder blob, your Renard.
Yep.
They fly slower.
I believe they can fly a little bit slower when they're flying at the minimum speed before stalling, if I'm not correct. Melanie might want to correct me on that.
So, yeah, they're flying our when they do a drop. So both of them are flying safe speed when we did the drop.
Okay.
Well, yeah, so I think using this data to inform drop mechanics and looking like that's something I thought about too, and chatted about with Tyler Forbes from the MNR is, well, like this can be a training tool for new pilots that have not done the Airtanker drops, is helping them understand, well, how does my drop footprint change when I'm dropping these different fuel types? He said it takes them about 3 to 4 years to really be able to predict how these different forested environments change their drop footprint. So I think there's a lot of useful information in these.
I believe that the last question of 2025 goes to Dave Martel. I think you should get somebody else to do the last one.
Very important work and a very important problem, and I'd like to go back to your reference to stacking drops. And this is going well beyond what you're doing, but suppose someday in the future, guidelines were developed that said, on this kind of fire, in this cover type, I want the coverage to be of this depth, therefore I need these kinds of overlaps. To what extent do you think it would be possible for the pilots to accurately drop to achieve those guidelines?
Yeah, that's a great question. Speaking of a non-pilot here, from looking at this data, I think it would be quite challenging. Like looking at the airfield data, they were say very good at hitting that cup grid, but looking at the canopy site, like there were drops where 10-20% of that drop hit the cup grid. So I think that's it's a natural constraint to doing this kind of research is the limitations of the pilot, and I think we have to take that into consideration that it's easy to sit here and be like, well, why don't you just put that whole drop footprint on the fire? But there's someone in that plane making real-time decisions, trying not to hit the canopy, trying not to crash the plane, that I think it would be quite challenging to achieve those objectives.
Thank you, Daniel. We will call it.